Okay, good afternoon, everyone. So I'm
recording in progress.
I think we've got somebody with their microphone there. If you wouldn't mind just muting yourself, that would be very helpful. Thank you. So for those who haven't met me, I'm Simon Hogg. I'm the head of the engineering department at Durham University, and I've been involved in CESI since its inception. What we've got for you now for this next hour, anyway, is, as you know, is a session jointly between Work Package 2 and Work Package 3. So we merged those two work packages partway through CESI to form the Energy Supply and Infrastructure joint package. And we've got this session just really giving a couple of flavors of some of the things we've been involved in during CESI in those areas. Tony Roskilly, and as you'll spot there is a typing mistake on the slide that you're looking at now. His name really isn't Roskilly, it's Roskilly. Tony's unfortunately elsewhere today, so I'm going to host this session on behalf of the two of us. So we've basically got the running order there. So myself first, I'm going to say a little bit about some of the modelling we've been doing for wind farm, and then we've got Andrew Smallbone kindly presenting on level. Well, you can see his title there, then Charlotte, and then it won't be Tony at the end there. It'll be Andrew again filling in for Tony because he's elsewhere, as I've already said. Okay, we are recording the session, so please be aware of that. And if you have any, we're going to have a Q&A at the end. So the session is an hour long. We'll try and get through each of the presentations in 10 minutes more or less, and then that leaves a quarter of an hour or so at the end for some questions. If you have questions, think of questions as we're going along, please put them in the chat. That is being monitored as we go through, and please will you also say who the question is for when you put them in the chat, so that we know who to address that to when we get to that part of the agenda. Okay, so thank you very much. So I'll jump straight into the first presentation, which is yours truly. I'm just going to in the next 10 minutes or so give a very quick flavour of some of the modelling work that we did under CESI. So this was done as part of the second co-evolution cycle when we were looking at the north of the Tyne region here. We developed a new modelling methodology for calculating the power output from wind farms in general, and then we applied it to some of the farms in the north of the Tyne region. So I thought I'd talk about that very quickly now to give you a flavour of that aspect of the work we did. Okay, so the first thing to say is fairly obviously from that picture there. For those of you that haven't been involved in wind generation previously, they interact. Okay, if you have a wind farm, you can't just view it as a collection of wind turbines operating in isolation. Depending upon the wind direction, there are interactions that take many different forms. So you can see very graphically there. This sometimes happens. There's a few of these pictures around if you look on the internet, where so that's a real photograph, and the climatic conditions are such that in the wakes themselves, condensation happens in the wakes, and you can actually get a real life visualization of the flow. And in that example there, you can see how the wind direction is aligned with the direction of the turbines, and you can see quite clearly that many of the downstream turbines there are operating in the wakes of the turbine upstream of it, and that has a significant impact on the power output that the downstream turbines can deliver. And it's not what we're going to talk about today, but there are actually farm level control strategies being developed now where you basically detune the turbines on the leading edge, so you take less energy out the wind for the leading turbines at the upwind end of the wind farm, and that then enables the turbines that are in the wakes further downstream to actually perform a bit better. And when you optimize that over the farm level, you can actually get additional power output from the wind farm by doing less with the upstream turbines and more with the downstream turbines in that way. So interactions are a key part of wind farm design and wind farm management. That's a LiDAR picture, so basically a radar but using lasers. They're used a lot in the industry now, and this is a picture of I think looking at the titles on the axes there, it's a North American wind farm here where this was done. But you can see the wind resource there for this particular wind direction has been measured with the LiDAR, and you can see clearly how this wind direction for some of the turbines, particularly the two on the left-hand side of the graph there. You can see how they align, and the wakes there of the upstream turbine has a significant impact on the wind resource approach in the downstream turbine. Whereas if you look at the redder colours between the turbines, you can see there are lines of flight through the wind farm in that direction where the turbines don't interfect the flow and the velocities are much higher there. So another example of how important this sort of interaction between the turbines is when you're calculating farm output. So here's a third slide on the same theme, really. So the graph at the bottom there, you've got normalized power on the vertical axis, and then wind direction pretty much going round through 180 degrees or so in this snippet. And you can see from the figures above how there are, for this regular wind farm layouts, there are a number of directions that the wind can come from where there's significant potential for interactions between the turbines, and that's borne out in the calculated result that you see at the bottom there, where you can see for some wind directions quite a significant, almost approaching, well, a 40% reduction in power output. Almost half the potential power output from the wind farm is lost due to these interactions between the turbines. You know, there are some directions there where the interactions are minimal and you get a reasonable power out the farm, but then in other wind directions this has a big effect on the power output. So really our piece of work that I'm going to talk about now was we developed a model for calculating this effect, if you like, and then applied it to some of the wind farms in the northeast region. So how did we go about developing that model? Well, the first thing you need to know is the power curve of the turbines itself. So this is manufacturer's data. So the way we did it was we actually accessed for the different turbines that we have in the wind farms in the northeast, we were able to get power curves for those individual turbines and use those within the model. So that basically tells you what a wind turbine operating in isolation will do for different wind speeds, and that's a typical characteristic curve there for a modern large onshore or offshore wind turbine. And the wind velocities at which things change are pretty much an industry standard now. So below about 3 meters a second or so of wind speed, so roughly double that to make it miles an hour. So below 3 meters a second, then the turbine is not generating anything at all. And then above 3 meters a second, up to about 12, 13 meters a second, usually 12 meters a second, there the power that the turbine produces ramps up as the wind speed increases. Once you get beyond about 12 meters a second, then the blades, that modern turbines that all have pitch control blades, so the pitching of the blades is controlled in a manner that limits the power output of the turbine to its rated value. So for this curve here, it's a 2 megawatt wind turbine, and the blades are pitching between 12 and 25 meters a second, such that even though the wind speed increases, the power output of the turbine doesn't increase. So that keeps the forces on the structure within acceptable conditions to give you a reasonable design life for the turbine by controlling it in that way. Above 25 meters a second, the wind is getting too strong really for the turbine to operate safely, and so at that point the blades would be feathered such that there's no net torque on the rotor, and the turbine is essentially stopped in very high wind speeds to preserve the structure. So that curve, typical of the generic form of all modern wind turbines now, they all look like that, and clearly the vertical axis there depends upon the rating of the turbine itself. To give you the current maximum numbers, Siemens Gamesa are just bringing what was originally a 14 megawatt offshore wind turbine to market. They've actually been measuring the power curve of that over in Denmark, and at the same time they've been tweaking it a bit, and they've now actually uprated it to a 15 megawatt wind turbine as part of that testing in the final stages of development. So that's the world's biggest wind turbine that you can buy at the moment. But typically for onshore applications, 2 and 3 megawatts are typical sizes for the wind turbines that you see, certainly when you drive around the UK. Okay, so that was the basically for a turbine operating in isolation. Now we need to think about how they interact and how we model that. And so the wake that's behind the rotor of a wind turbine, as that moves downstream with the air velocity, it's going to spread. So the wakes actually increase in diameter with distance from the turbine. You could sort of see that in the photograph that we started with on the first slide there. So there is the Jensen wake model. That was something that was actually developed in the 1980s, and it's still sort of widely accepted as a good first order model for predicting how wakes grow as you move downstream from turbines. And you can see the model there in the expression on the bottom of the slide. So we used that model within the CESI work to model wake growth with distance downstream of the turbine. So that was the power curve told us how much the individual turbines would deliver for a given wind velocity. And then in terms of modeling the wakes, this was the first step. And then there's a second important step in terms of then modeling the effect of the wake on the turbines that are downstream of the upstream turbine. And that is the proportion of the wake. You need to be able to work out the proportion of the wake that actually interacts with the downstream turbine. So in this figure here, you can see a rotor on the top right-hand side, and then a wake of an upstream turbine on the left-hand side. And the diameter of that wake is larger than the rotor diameter, because that's grown a bit with the distance downstream that the current turbine is from the one that produced the wake in the first place. And in the alignment between these turbines is such that only a proportion of that wake is interfering or is interacting with the turbine downstream. So the model that we developed also needed to have some way of calculating the proportion, if you like, of the upstream wake that actually interacts with the turbines downstream of it. So we developed mainly based on geometry. So we have that expression at the top of the slide there, which allowed us to calculate that shaded area on the figure there on the left-hand side that you can see. And then the task then of calculating the actual wind velocity that a downstream turbine will see, affected not just by one wind turbine upstream of it, but by all of the wind turbines that exist upstream of the turbine that you're interested in. We ended up with an expression such as the one at the in the middle of the slide there, which basically allows you to sum together for all of the end turbines upstream of the one that you're interested in. You look at the velocity deficit due to the effect of the wake, and that beta value there which reflects the proportion of the rotor area that's affected by the upstream wakes. Add all of that up in that expression, and in that way you can come up with a velocity, an average velocity that the particular wake that you're interested in actually sees. And then once you've got that velocity for that downstream turbine, you can then go to the power curve and work out what power that turbine is going to deliver. So that's all well and good. But then the third and final part of the model was clearly as the wind direction changes, then that picture is going to change. The extent to which upstream turbines interact with the downstream ones will be different for different wind directions. So within the model we developed, we also implemented a rotating coordinate system, which is shown graphically in this slide here. So the pictures on the left hand side show how for different wind directions the interactions between the turbines are going to be different. The turbines themselves will always be yawed so that when they're operating, they're always facing into wind. That's shown in the picture on the right hand side. But the alignment between them will depend on wind direction. So basically we developed the third part of the model, which was once you knew where all the turbines were relative to each other, and that was part of, so the inputs to the model would be the power curves from the individual turbines and the locations of the turbines relative to each other. Once you knew that, then if you selected a wind direction, you can write down a coordinate system that is aligned with the wind in the way that's shown there in the figure, and then the locations of all of the turbines can be then expressed within that coordinate system, and from that you can then get the geometries which allow you to calculate the wake interaction effects and ultimately the power output of each of the turbines. So that's a very simplistic flow chart showing the process itself. So you select a wind direction, you know where the turbines are, so you use the rotating coordinate system to align with the wind direction so that you can work out where the turbines are relative to each other relative to that particular wind direction. Select a free stream velocity and then use the shadow wind model and the Jensen model to calculate the power output of each turbine, and then sum all of the turbines to get the overall farm output and iterate around those loops for each wind velocity and for each wind direction. And if you do that, eventually, you'll end up with a mapping, a surface plot, if you like, and I'll show you some in a moment, that covers the output of the farm for any wind speed or any wind direction. So these were the onshore wind farms there in the table that we identified in the North of Tyne region that we looked at. We also looked, as I've said at the bottom there, at the Blythe offshore wind farm as well. So I'll say just very quickly now in my last couple of slides, I'll say something about one of the onshore turbine farms, and also the Blythe offshore wind farm. So that's the result there for the Ray onshore wind farm, which was in that previous table. It was a 16 Senvion 3.4 megawatt wind turbines. The researcher that did this work actually used satellite positions. You can see the satellite photographs. You can see one on the left-hand side there of this wind farm to then locate the turbines relative to each other. That went into the model. And then when we ran through the model that I've just described, you can see the output from it there, which is that surface plot with the two horizontal axes being wind direction and wind speed, and then the vertical axis being the power output of the farm. So 16 times 3.4 megawatts gives you something like 54 megawatts in total maximum output. And you can see from the surfaces there how the interaction effects produce these undulations in the slope surface of the carpet plot there, which reflects the different wind speeds, different wind directions, the different interactions between the turbines in that particular layout. Probably a more stark example is Blythe. Sorry about the picture on the left-hand side there, but the Blythe offshore wind farm, there's only the existing array. The other two arrays aren't there yet. The existing array, the one that's in the dark blue, consists of 5 8 megawatt MHI Vestas turbines, so 40 megawatts in total. And you can see those turbines from Blythe or from Tynemouth Beach even. They are all more or less in a line, as you see in the figure there. And the result from the model reflects that, in that you can see these two very sharp deviations in the contours there when the wind is aligned in one direction or the other with that row of turbines. For all of the wind directions, you tend to pretty much get the very little stroke zero interaction effects and the maximum output. Okay, so that's what I had for you, just to give you a very quick flavour of what we did in modelling wind farms under CESI for the North of Tyne region. I think now if I hand over to Andrew for the first of his presentations, he'll take you through that. So Andrew, if you can, I think I stopped sharing my screen, so if you can share yours, brilliant.
Can you see that all right? Yeah.
I can see that. Good, yes, thank you.
Okay.
Over to you.
Right, thank you very much, Simon. So yeah, this was some work we carried out for CESI in 2017. I was just refreshing some of my memory of doing it, but yeah, so we were looking at the levelized cost, and we did a levelized cost evaluation for energy storage technologies. So I'm Andy Smallbone. I'm an associate professor at Durham, but when I did this, I was at Newcastle. So the context of this is obviously from a future energy systems perspective, energy storage is extremely important, and it could be said that it enables net zero. So what we were interested in was to explore some of the key technologies that will unlock that and understand their cost and their impact. So it's got two roles, really. Energy storage first is to enable the greater deployment of renewables and thus to achieve net zero more readily, but also potentially that energy storage could be used to displace the role that fossil fuels hold in delivering resilience and flexibility. And what we wanted to really get to grips with was to understand some of the challenges around that. So there are many forms of electricity energy storage, and we wanted to understand kind of high-level questions like which one is cheapest, which one is the most deployable, what's that same world going to look like in 10 years' time? So to try and understand some of those things. If you look at that schematic at the bottom there, you can see the terms that we were looking at the energy storage in that actually it's, and if you look across the technology set, actually whilst the input and output of electricity, there's lots of different ways that you can go from the input to the output. So in almost all cases, there is some form of transformation of that electricity into a form that is suitable and scalable for storage. And there are different factors associated with that. It could be some losses, so therefore some efficiency losses through the process. It could be the cost of that transformation in terms of the unit costs or the OPEX costs, as well as the lifetime of that particular unit. When it comes to the actual storage itself, it's not always stored in electrical form. It can be compressed gas or heat or whatever, but in doing so, you're storing and you're losing energy as you're storing. Those storage units have cost. They've also got specific lifespans, and as well, some of them scale linearly and some of them scale in other ways, which can be much more favorable when you go to the gigawatt scale than you currently see maybe currently on a sub megawatt scale. So there's lots of different factors in there. And then, of course, then when you go from storage, you go back to electricity, then there's another set of losses, another capex and a lifespan. So in bringing that all together, you've got a system which is doing storage. It's got efficiency losses, it's got different costs that come in at different parts of it. They scale in different ways, and they're all over the place in terms of technology readiness level. We wanted to try and understand how that all fitted together and understand how compatible some of those are with existing energy systems. So we basically went out and looked at kind of core technologies that were relevant in that time. And I think what we did was we probably picked the most important ones, and they're still the most relevant today. So those were the pumped hydropower, 3 forms of electrochemical batteries. Obviously, the most common now is the lithium ion, I think, in that space. But we were also looking at 2 forms of compressed air energy storage. The diabatic version had already been deployed, and now we're seeing increasing amounts of adiabatic, so those were quite sensible. And also we're seeing much more power to gas technologies. It wasn't really that, wasn't many people talking about that in 2017, but actually when we picked out the hydrogen and the methane option, I think they were kind of considered in parallel, but I think the hydrogen option is a much stronger case now. But what we were really keen on is that in parallel to this, we within the team, we were working on a technology called pumped heat energy storage, and we wanted to think about how this particular technology, how that sat alongside some of these more common and well discussed storage solutions. We've published all this work, so if you want any of the info, you can follow the link to that down there. I'm sure we'll share the slides in good time. So what we were doing is we were working on a concept on pumped heat energy storage with the Energy Technologies Institute from about 2016. During the time of that development, there was a major investment by Malta, which was funded by Silicon Valley into the same kind of technology. And they were developing a 100 megawatt kind of scale system. And over time, that's evolved into an area now of energy storage research called Carnot Batteries. So during that period of time, we were involved in a lot of this, and a lot of the work that I'm presenting now actually has shaped a lot of that. So the system that we were looking at, and the ones that really are discussed really in Carnot Batteries is not dissimilar to this, but the one I've done the analysis here on is a system where you take electricity from the grid or renewable energy source, you use that to turn a motor, which powers a system here, which is running as a heat pump normally as a charge. So as a heat pump, you push a working fluid around the system, and that heats up a hot thermal store and cools down a cold thermal store. When you decide that you've charged the system enough, you stop doing that, and then discharge system, you basically run the same technology in reverse. You use the temperature differential between the two stores to power the rotating machine, which brings electricity back into the wider energy system. You can do that on demand. And what we really wanted to understand is actually the storage medium in here is tiny amount of money and very scalable, but you need to have all of the costs associated with everything else to get that to work. So we wanted to understand how that all came together, really. So that what we were being asked was, how do things like this energy storage technology compare with others? What's the round trip efficiency? So, and we wanted to push the discussion in and around what's the cost of storage rather than the efficiency, because our system was cheaper overall, but it was less efficient, and we wanted to understand that a bit more. The challenges we had was that the technology we'd built was a low technology readiness level. It was a first of a kind system, and we weren't that sure how to scale up. And the common question we were being asked is, what is the nth of a kind cost? So what is not the first system? What is the 10th? What if you've deployed this at large scale? What potentially would energy storage from this kind of solution look like? So we utilized the levelized cost analysis, and we did that in collaboration, strong collaboration with the Fraunhofer Institute, who'd already built some detailed libraries of tools and models that can unlock some greater understanding of some of the costs. And they had a lot of the data on some of the wider systems. So they supported us in developing our own levelized cost analysis of this particular technology set. What we went out and we did was we decided a particular size of system that we were interested in. And just for simplicity, it was a 2 megawatt system and stored for 8 hours. But I think if I was to redo this now, I'd probably add another 0 or 2 zeros onto that system to really understand what its impact would be. But that's where the market was back then compared to where it is right now. So we went through the whole component of the system, and this slide kind of shows some of the details on that. But I guess just to summarize, really, we went out, we looked at each component, we worked out what would that cost based on the first design, and then what if we built that and started to mass produce that particular component. And then we verified that against concepts like or technologies that were similar that had already reached an nth of a kind. So a good analogy here is that our reversible heat pump was not dissimilar to a diesel engine. It wasn't the same, but many aspects were the same. So you could use our understanding of our system that we've been working on and could compare that with the cost of the diesel. And that gave us some rationalization of some of the numbers that we ended up fitting into the analysis. And we also accepted we didn't know everything, and we put uncertainty on a lot of the things in order that we could understand some of the key sensitivities. In terms of CapEx, the plant there ended up costing between 1 and 2 million euros for the system. And we got to understand and explore and understand the impacts of efficiency. And actually, it wasn't that significant, the efficiency. The main cost was actually the cost of the heat pump. And the more work you did on improving the cost of the heat pump, the better return you got that on the overall system costs. When you then compared that across the technology sets that I was talking about at the beginning, and here we did an analysis of a 100 megawatt plant and storing for 4 hours, you can then start to see the comparison of these different groups of energy storage technologies and which kinds of ones would likely to end up with most cost-effective forms of storage. And I guess they've been ranked really around these numbers here. So the first one here is pumped hydro, which was on relatively the cheapest. The pumped heat solution we were looking at here, you can see there's quite a bit of variance, but overall it was one of the cheaper technologies. We've got the compressed air storage solutions in this range here, and then we've got batteries in over different time scales, so the 2030 costs and then current costs. But you can see up here, this is the power to gas technology sets. I think the key output from this analysis really was, if you start to change these numbers here, stop storing for maybe 40 hours rather than 4 hours, then maybe some of these cost of pumped or hydrogen technologies relatively they become a lot cheaper than they are in this context. But we built the model, we could understand how all of these things came together. But I guess our conclusion here really was that even in the worst case scenarios, that there was a cost-effective solution around the technology that we were exploring. Okay.
Okay,
so
brilliant.
Thanks
For that. If you can stop sharing now, and we'll move on to Charlotte, who's going to tell us about techno-economic environmental analysis of a smart multi-energy grid utilizing geothermal energy supply. And Charlotte, if I can ask if you can do what Andrew and I have both failed to do, and that is stick to the 10 minutes if at all possible, then we should be able to still have time for questions at the end. Thanks.
Thank you, Simon. I will do my best. Can you see that okay?
Yep, got that.
Brilliant, thank you. So thanks to CESI for inviting me back effectively to give this talk. So I stopped being a CESI researcher about 3 years ago. I now work for the Coal Authority. We're involved in deploying ultra low temperature geothermal systems across the UK using heat pumps and using the water within disused coal mines as the energy supply. This piece of work we did as part of CESI. So I was working with Simon and John Gluyas in the work packages, one of the work packages from Durham. And I thought a good way to kind of showcase what we did was to focus on one of the outputs, which was the paper. And I've got a link to the paper at the end. So if anybody wants more detail, because I'm not an expert modeler, I work with collaborators on that. So Adib and Hamid at Newcastle, and their links are in the back there as well in the paper. So any questions on specifics of the modelling, you can ask them. But I'm giving an overview of what we did. So the aim of the project we were working on was to develop an evaluation framework. And this involved a kind of multi-vector energy network. So we had a range of energy inputs to the network. And it was operating as a smart multi-energy grid. So thinking about the kind of operational characteristics of that grid. And this was enabled to consider simultaneous supply of heat and electricity with both varying demands and varying production from some of the renewable sources, which are obviously linked to environmental conditions. So there was a heat and electricity grid that was modelled. And this was slightly different in that it included geothermal options, and I'll talk about that in a bit more detail later, because geothermal is often not included in things. This was geothermal for heat, not for electricity. And it was focusing on decarbonising heat supply, and we were to test it also using a real case study. So that was kind of the aim of the project, to develop this evaluation framework, which would evaluate from a technical, environmental and economic perspective. Why we were doing this was basically looking at the options for decarbonising heat demand. So this is linked to climate emergencies. More recently, this is relevant because of the energy crisis, the cost of gas, and also things to do with energy security. So if you can produce it locally, then you take a bit more control over your energy supply, as well as the need to reduce carbon emissions. And as I've mentioned already, this included geothermal, but it also included having a network that had wind and PV feeding into it. And we looked at deep and shallow geothermal, which I'll differentiate in a moment. We compared it with all gas and all electric counterfactuals. And as I mentioned before, geothermal is often omitted from these kind of studies. Because it produces heat, it's maybe not been thought about so much. The UK geothermal resource assessment that was done in the 1980s in response to the oil crisis concluded that, yes, the UK does have geothermal resources, but they are better geared towards heat supply with a modest potential for electricity generation. So there are a couple of projects in the southwest being drilled for electricity at the moment, but generally the UK's geothermal resources geared towards producing heat. So it's getting the message across to people more widely that you don't need volcanoes for geothermal, you can use it. And it is available in most countries, so you don't have to have be near a plate margin, have these really high temperature systems. So looking at what we put into the model, so we put deep and shallow geothermal into the model. So the deep stuff was effectively heat that could be used directly without being upgraded by a heat pump. So, you know, you're looking at temperatures of 70, 80 degrees, something like that. And the shallow was differentiated by a temperature that you would need to use a heat pump with to make it meet the kind of demand temperature. The source of all this heat is from naturally occurring radioactive processes going on within the Earth. And the key thing for these projects, whether you're looking at deep or shallow, is that water is the energy carrier for these. So you need to have water down where your reservoir is so that you can take that water, bring it to surface, get the heat from it and put it back to be reheated. In future, most systems at the moment use water as the energy carrier, but in future there's no reason why this couldn't be something like CO2 as well, and that could be circulated as the fluid to scavenge the heat. So that's one area of research that's moving forward on these as well. This study didn't include CapEx, but I just wanted to mention that there is a bit of a trade-off, obviously, because you can go deeper with the deeper geothermal systems, and the benefit of that is you get higher temperature water. You might not need a heat pump, but then your drilling costs are higher and your risks of maybe not finding water at depth, because we don't know as much about subsurfaces at depth, are a bit higher. So there's this trade-off between the shallow and the deep systems. There's a system in the UK at the moment that's been running, developed as the result of that survey that was done in the 80s. That's at Southampton and 1.8 kilometres. So that's deep geothermal producing 72-degree water. That's been running for quite a few years now. We've also got a mine water scheme that's been producing around about 4 megawatts of heat. So it's actually bigger than the deep geothermal scheme. That's near Gateshead, and that's using water within the abandoned mine to keep a wine warehouse at the optimum temperature. And we used these kind of geothermal scenarios for this model and for this project, but there's no reason why you couldn't use a different type of geothermal reservoir, such as an aquifer. We just used the mines in this case because they've got lots of tunnels in them. We know lots of water flows through them. And we had quite a bit of data from them as well. So the approach was to, in order to develop this model, for me, and especially with what I'm doing now, it was quite liberating because we didn't have to worry about capital costs. It was like, let's just assume all these systems are there doing their thing, and we can evaluate them from a technical, economic and environmental point of view. So it's more on the kind of OPEX side than the CapEx. The technical parameters were things like energy supply from the upstream network, and that allowed an evaluation of supply security and self-sufficiency to be made. The economic parameters, the operational cost, and the cost if you had to purchase alternative energy from the upstream networks. That enabled us to quantify cost savings from increased integration of the energy sources and more use of local generation, and the impact of using more of what you could produce locally too. Then the environmental parameter was obviously the CO2 emissions, compared to kind of counterfactuals and again from upstream imports if you were relying on those. So there's a block diagram of the algorithm there. It's explained in a lot more detail in the paper. It shows the various inputs and also the couplings between them, which is what we thought about, you know, how they might work in this network. And so we got this technology simulation engine, which kind of is how it works first, and then that allows, once you've got that kind of, when you've worked out how they're all going to interact and how they might work with each other, that can then drive the technical evaluation. And then the economic and environmental analysis is then performed based on what the technical parameter outputs are. So you're running the model with all these systems in place. It's giving you some kind of technical results in terms of energy produced, and then you can use that to do the rest of the evaluation. So that's how it was kind of combined. And there was a whole range of scenarios tested, from all electric to all gas. CHP and geothermal were included, and there was combinations thereof within that. Case study that was used a lot in the CESI work by a lot of the different work packages was Findhorn, this kind of eco village up in Scotland, which already had some wind farm and PV. So there was data available from that point of it. We supplied the geothermal data from some of our experiences from other sites. And so the results that we found when we ran this model, so the results here, the kind of beigey colour on this shows the electricity, and the heat is represented by blue, and that's the loads for each scenario. And you can see on the left the different kind of scenarios that were modelled. And you can see there that for configuration 4A, which included the high temperature geothermal, i.e. geothermal being used direct without a heat pump, has by far the lowest technical, economic and environmental parameters. So that came up as the best one overall relative to the other configurations. And that was regardless of an increase in wind and PV. I think essentially it was due to the cost, the free cost of the fuel for this being a geothermal source. So you can, the paper gives a bit more description on each of these, but you can see roughly how they're each performing. And you can see that if you're looking at from an economic standpoint, you can see that the all-electric scenario, unsurprisingly, has the highest because of the high fuel costs and things. So it's quite interesting to look at how these different configurations played out once the model was run. So we found from doing the most efficient, cost-effective and lowest carbon was the high temperature geothermal option. And the geothermal uses available technology, and it's something we can do now to decarbonize heat, and it's, you know, it's what I've moved on to be doing now. We are doing it now. It can operate effectively alongside other low carbon energy sources, and it is, you know, can give a continuous energy supply or heat supply. So it is quite good for base load. And the conclusions we had are specific to this case study, but I think the model that was built could be used for other areas, and it'd be very interesting to see how that graph of how the different configurations conformed, how those results change if you're looking at a different site, maybe with different demands and different inputs. There was some future work identified in the paper as well. So, you know, looking at this model for a wider region and also at national level, including things like storage into it in future would be good. And then also coupling in things like investment planning and optimal scheduling of the components and any storage devices as well would be something that you could build into this to extend it in future. So that was a very quick run through. Hopefully that was to time, Simon. And there's a link to the paper if you'd like to know any more about it. Thanks for listening.
Okay, thank you very much, Charlotte. If you can stop sharing now, that was brilliant. Thank you. So now for the final presentation. Yeah, it's not Tony Roxley. It's Andrew again presenting for Tony here, and he's going to tell us about the hydrogen hub infrastructure and storage work that is related to CESI. And Andrew, if you can ask, just please keep an eye on the time so that we've got one question in the chat there, so that we have time to take some questions at the end. Thanks.
Okay, right. So yeah, this is about a hydrogen hub infrastructure and storage, which was a sub-package we were involved in a bit later on in CESI. I think the first thing really to say is that the world has changed quite fast in and around the topic of hydrogen, and it's changing in lots of renewable energy technologies. But I think this slide here, I won't go into too much detail, is basically showing that electrolysis and hydrogen is going to see the most rapid change and rapid rate of growth across all of those particular things, and actually its potential of where that's deployed and all of the technologies that kind of underpin the hydrogen economy, where those are deployed, are really interesting. And that's the kind of heart of what this project was all about, really. So I think I'll skip much of this just for time, but basically hydrogen has become a very, very important and critical topic. It's gone from niche to mainstream very quickly. You can see in this diagram that we produced here on the side here, there is lots of potential end users for hydrogen, but hydrogen itself can be produced in lots of different ways. And I think the consensus is broadly that green hydrogen, which is what's shown here, which is renewables powering electrolysis to produce hydrogen, is probably the best and scalable and greenest and etc., etc. But the key thing is that it can produce hydrogen directly from renewable energy, which in itself could actually bring some resilience to the electrical sector. when it's not needed by the electrical sector, it can be used to heat buildings, power transport technologies, as a commodity for the industrial sector, or as a heat source for heavy and high temperature services that are required in the heavy and manufacturing sectors, but also can be transported in the gas network, which will have huge cost savings for energy distribution. And of course, it can be stored and it can be used in a different part of the season. So there's lots of opportunities in around it. It's just settling down as to what those opportunities really genuinely are. But overall, it's a very key intermediary in whatever net zero looks like. So what we've been looking at is specifically is where do you do things like electrolysis or conversion back to electricity? And can that be used to make this system more, on a system level, more efficient and more cost effective? And one area that we've been looking at is what we've been kind of terming a hydrogen energy hub. I think the title of the slide here shows a future integrated hydrogen energy system. Basically, the system we've been modeling and analyzing, I guess, starts with a connection to the future gas network, for example, where that mixture of gas is either natural gas, it's either hydrogen, or somewhere in between as we transition to a more hydrogen economy. And the rest of the system here has to be resilient and flexible enough to be able to handle that. And the way that you do that is you use a technology called a solid oxide fuel cell. So a solid oxide fuel cell is slightly different to the kind of fuel cells that we see quite commonly now through various activities in transport, for example. Solid oxide fuel cells work at higher temperatures, and they can reform natural gas to produce hydrogen within their cycle and process itself. And that therefore produces electricity in the conversion process, which can obviously be deployed for various things, including powering homes, but it also can be stored in the form of in a battery, but also produces enough heat that actually there's other potential end users for that heat. So any outputs from this solid oxide fuel cell can be burnt, producing even more heat potentially, and that heat then is used here to preheat the air going into the fuel cell stack, to preheat the hydrogen or natural gas going into that fuel stack. But any waste can be utilized here to produce heat for a local heat network, for example. And this means that this fuel cell can be used as a combined heat and power system. And what we wanted to look at was actually the potential of this technically, but also economically across this solution. And when you analyze and you scale here to around a megawatt kind of scale system, you can see that the different systems here, whether they're powered here by natural gas, here shown as methane, or hydrogen, you end up with part of it is electrical power, which is the red, and then somewhat of the rest of it here is heat. So this additional is the value from running the system as a process which produces two sources of energy. Obviously, this increases the efficiency, which is one of the negative aspects of utilizing hydrogen, but pushes the efficiency over 80%. Now you can take those kind of analysis and you can add a technical and you can add the economic aspects of it. And you can take things like costs from the 2030 timeframe from various sources, including some of our own work. And you can work out and show here that actually when you take current gas prices and you utilize green hydrogen powered by wind, and you deploy that, actually it's not really that much more expensive than where we are currently, and there's lots more potential to take this forward. So by utilizing the heat from these kind of processes, by deploying locally within local infrastructure, you can actually get a huge much more value from these kind of hydrogen energy systems. So really to conclude there and giving us enough time for questions, what I've shown here really is that, and the work has shown that things like solid oxide fuel cell systems can offer a technically and economically viable option for deploying hydrogen into local communities. So I guess more generally across our work, across a number of other projects, we're showing that actually co-locating hydrogen production or hydrogen conversion within local and next to local heat demand centers is a very cost-effective option to reducing the barriers and the cost for net zero. Okay, I think that's it from me.
Okay, thanks very much, Andrew. Well done for recovering our time schedule there a little bit. So if I can ask the attendees, then please put questions in the chat and we'll take them. There is one in there already from Alec, which was about my presentation at the start there, where he's asking, is the wake assumed to have no energy? Well, no, the wake is depleted energy. So that Jensen model that I mentioned in my presentation, it allows you to calculate a velocity deficit, if you like. So so the wake has the turbine itself will take a certain amount of energy out of the flow, and so the energy that's left in the wake is then not zero, but it's less than obviously the energy in the air that's approaching the turbines. And then as that wake spreads downstream, then the velocity in the wake gets lower and lower, so the energy is diminishing further, but it's not non-zero. So the model does take into account essentially the energy removed by the upstream turbine, and then how it is diminished downstream as the wake spreads, and the energy in the wake is spread over a larger area. So I hope that answers your question there, Alec. Just having a look. So there's this new question just in then from Mansouri regarding wind modelling. Oh, it's another wind one. Has the model been validated with any real data available? If it is, well, the power curves that are underlying the model, the power curves are manufacturing data. So that is real test data. So what happens is when wind turbines come to market, a prototype turbine is tested in isolation. So I actually, just a few weeks ago, I visited a test site at I think it's pronounced Østerild in Denmark, where they had I was mentioning about the Siemens 14 megawatt turbine in my presentation. Well, they actually had the turbine on test there for its power curve. So it takes many months to actually produce a power curve for the turbine. So obviously the manufacturers have predicted what it should deliver, but before it comes to market, that is tested. So they basically run one turbine in isolation, and over many months, so they get many different wind conditions, many different wind speeds during that period of time, and produce and validate the power curve with real site data in that way. So at the heart of the model is validated data, the power curves themselves. The rest of the model is they're not mainly geometry and the Jensen model for calculating the wake effect. We didn't validate our model against any wind farm data because we couldn't get our hands on any, but the results that we got from it looked consistent with other studies, so we were reasonably confident that they were a fair reflection of what was going on. Okay, Laura, thanks for a question in there for Charlotte. Charlotte, do you want to take that one? I think you can see it in the chat for yourself.
Yeah, thanks, Laura. Yeah, we've got a fairly good idea of what the temperatures will be, because we know due to the geothermal gradient of the Earth, so that works all the way from the core to the crust, so temperature drops all the way along that distance. We know that in the UK, for example, where we've been basing these studies, the temperature usually gets hotter by 25 to 35 degrees for every kilometre you go. And depending on where exactly you are in the UK, we can know whether you're near the 25 or 35 degrees. So yeah, we are finding that the temperature predictions are fairly accurate. The thing that's less accurate is knowing whether there's water down there for the deeper schemes, which is more challenging.
Okay, thank you. Okay, we've got any more questions for anybody in the audience?
I've got a more general one for Charlotte, if you don't mind. You touched on it briefly, but I was just wondering how the research and skills that you learned from your time at CESI have been used in your current role, or if they've been applicable. So yeah, more general question for you, Charlotte.
One of the projects we're involved with at Gateshead, which is due to be operational soon, we're setting up a living lab there. So we're going to drill some more boreholes aside from the ones that will be used for the actual scheme to be able to monitor that network. And it already has a 3 megawatt CHP scheme feeding into it, and it'll have another 3 megawatts from mine. So I think, you know, something like this model, we can actually probably do another version of it and run it on that site once we've got a bit of data out of that, which should, you know, happen over the next year or so. And I think for me personally, because I'm a geologist by background, working with the electrical engineers on this, I learned a lot from doing that as well. So I think more broadly, it's given me an oversight into some of the other disciplines and how they feed into what we might be doing, especially if you're wanting to integrate heat and electricity. So that was very valuable experience, and you meet some great people as well.
You've got another question for you there, Charlotte, just from Andrew, just popped into the chat.
So on offshore assets, so one of the other things we did during the CESI project, we looked at the Beatrice field. So we looked at offshore oil production areas, and that was also been done by Alison Auld, a former student of both Simon and I. She's published on it if you're interested in this. But we have looked at repurposing oil field infrastructure offshore and onshore for geothermal. So it's something we're thinking about, whether you would go and drill offshore directly for geothermal. As you say, it's probably too expensive at the moment when you've got the resource onshore and heat doesn't travel that well. You need it to be nearer to the demand. But there is that opportunity to repurpose infrastructure. And if we can do it for the mines, which I think probably have less economic value than the oil field infrastructure, then there's no reason why it couldn't be done for that too.
Okay, brilliant. Thanks for that. Andrew, you haven't had any questions yet. Let me ask you one though. Just a very, put you on the spot, just a very generic one about hydrogen, because it has, as you said in your presentation, it's really only in relatively recent years that hydrogen has emerged as the probably arguably the most popular vector for energy storage moving forward. Why do you think that is? Why do you think it is that hydrogen has suddenly come out the pack as the arguably the most favourable form of energy storage?
So one thing Theresa May did was she announced net zero, and I think this was the catalyst for it, because until that was said, then it was like net 20, or you know, people could get away with it. So basically everyone was looking at each other in different sectors thinking, I'm the most one that I don't have to decarbonize, mine's the most difficult sector. So they were all kind of not doing anything, and all of those people, they're the people that need hydrogen the most. And so they've come to terms with that idea and they've gone for hydrogen, and then that's unlocked it. I think that's fundamentally why. Brilliant. And that's the big change, I think.
Excellent. All right, well, on that forward-looking note, anyway, that takes us more or less exactly to 3 o'clock there. Thank you to all of the attendees to this session. I see that we held you all until the end there, which is always a good sign. And thank you from me to all of our speakers and to those from the CESI team who helped us put all of this together. So thanks a lot, and I wish you all a very good afternoon.
Thank you, everyone. And also just a note from me that the CESI event series is continuing throughout the week. So if you are available at 10 a.m. tomorrow for energy demand and 2 p.m. tomorrow for a talk on demonstrators, then you are welcome. But hope to see you all soon throughout the week, and thank you again.
All right, thanks everybody.
Thank you.